here for organizing this really nice conference, and thanks to Mandy also for well, for many things, for her talk, for being my most frequent collaborator, and for inviting me to this session as well. So I will talk about this. This is joint work with Mandy, but also with Javier Navarro. And we already introduced a lot of the concepts and some information that I will use, but just to fix the notation. This is going to be a finite group. And I will denote by I or R of G a set of complex irreducible characters of G. So I'm going to talk about different primes, and if I will try to say it every time that I mention them, but if not, P and Q are going to be prime numbers. And capital P will denote zero P subgroup of G, capital Q will denote a zero Q subgroup of G. So I'm going to talk about blocks, principal blocks, and also Mandy defined blocks in the way that I want them to be defined for this talk, but just review this. So we see blocks as subsets of the set of irreducible characters of G. So if we have two irreducible characters in G, we say that they are linked if the sum over the P random elements of those elements of the group for the non-divisible P is equal to 0. So this, as Mandy said, defines an equivalent relations in the set of irreducible characters of G, and or a graph, if you want to see it this way, and the connected components of this graph are the Brouwer P blocks. So, for notation, the principal block is the block containing the trivial character. The principal P block contains the trivial character, and in this talk, I'm going to talk about different primes. So I will try to make the prime explicit in the notation. So I will denote by P of G the principal P block of G. So we also know that to each P block we can associate a conjugacy class of P subgroups of G, which are the defect groups of the block. And these have, so if B is a P block of G, and B is a defect group of B, then we know, as Mandy said, that the values of the, well, the degrees of the reducible characters in the block are related with this number, the P part of the index of the defect in the group, and this is exactly the minimum of the P part of the degrees of the characters, sorry, in the block. And the characters attaching this minimum are the height 0 characters. So of course, if we deal with the principal block, we always have a linear character here, the trivial one, so this is just 1. So what we are saying is that the defect groups of the principal block are the zero P subgroups of G. So that's why it's natural when we deal with questions of zero P subgroups to go to the principal block and try to study what happens in there. Okay? I think that this is what the notation will be. I will try to use the blackboards as well as Mandy, but I'm making no promises. So this is, I said that this is the way that we like to see the blocks, at least in this work. And a reason to do that is that in this way, we are kind of forgetting that we are coming from modular representations. So we can wonder what happens if instead of considering just one prime, we consider more than one prime. And actually this is also kind of a classical question because Brouwer itself already tried to generalize his theory of Brouwer p-blocks to involve more than one prime. And in fact, for pi separable groups, there is a nice theory of pi blocks. We have analogs from sorts of p-blocks for these pi blocks, where pi is a set of primes. Okay, so we also want to consider different primes, but we don't want to generalize the concept of p-block. So we are still dealing with Brouwer p-blocks, but the idea is that we want to study p-blocks for different primes at the same time. So the question would be, can we say something, and I'll try to make this more precise now, on the PQ structure of G from the interaction between P blocks and Q blocks. Sorry. And what do I mean by this? So, Mandy also said a classical question was, can we detect from the character table if the CLO is abelian? No, that's a classical question on CLO is abelian. Well, a good question for PQ structure would be, can we put some conditions on the P blocks and Q blocks in such a way that we always have a CLO P subgroup and a CLO Q subgroup commuting, for example? That would say that we have nilpotent whole PQ subgroups, for instance. So this kind of questions is the one that we want to deal with. Okay, so now, I actually think that I will use the last 10 minutes of my talk to introduce our results, and first I want to give some examples in the literature. So the first example that I want to mention is Brouwer's High-Zero conjecture for two times. So also Mandy talked about Brouwer's High-Zero conjecture in her talk, but just let me recall what this conjecture said. So we have a P block of T and a different group of B. Then this conjecture says that T is abelian if and only all the P parts of all the degrees of irreducible characters in the block are the same. No? All of them are of height 0. I need to keep this way. For all the characters in the block. This is the same as saying that all the characters in the block are of height 0. Well, there has been some progress in this conjecture. I don't want to go into there. Mandy already told us. But one that I want to mention is that this is no longer a conjecture, but a theorem in one case, which is the principal block case. So this was proven by Male and Navarro. So Brouwer's High-Zero conjecture for the principal block. Let me rephrase what that says. In the left-hand side, we will have that the degrees of all the irreducible characters in the principal block are not divisible by P. And here we have that the CLOs are abelian. So this is here now. It was proven using the classification of and I want to introduce this particular case of the Brouwer's High-Zero conjecture because these two same authors, Male and Navarro, gave a generalization for their theorem in the case of 2 prime. Let's see how this works. So first the conjecture. 2020, that the following should be true. So we want a version for P and Q of this theorem, and on the left-hand side they said that should happen that P does not divide the list of all the reducible characters in the principal Q block of G, and at the same time Q does not divide the degrees of the characters in the principal P block of G, and on the right-hand side, what we have is that there is a zero P subgroup and a zero Q subgroup commuting. Okay? Why is this a generalization of this theorem? Because if we take P equals to Q in here, then we are recovering Brauer's-Height zero conjecture for the principal. So some comments on this conjecture. They prove one direction, they prove this direction in the same paper. And actually they reduce the converse direction to the inductive and conditions. Very recently, this direction was proven in a different way by some other authors. So this was proved by Liu I don't think this has been proved yet, but maybe it can be proved. So this is not a conjecture anymore, but a theorem. And this is what, at least for me, a nice version of these questions on PQ, because it works without solvability conditions. Okay, but the thing is that works for principal blocks, and we can wonder, okay, we have a version for arbitrary blocks that we believe that it's true, although we still don't know. And the version of this theorem also for non-principal blocks. And well, the natural translation to non-principal blocks is not true. So we know that this at least has not a direct translation to non-principal blocks. So last thing that I wanted to say is that if we input some solvability conditions, so in particular if the group is PQ solvable, then this is true without, for any block, not just for principal blocks. And this is a common fact of the examples that I want to mention. So either they work for the principal block or for arbitrary blocks, but we need to put some solvability conditions. Okay, so this was the first example. Now, the second example that I want to mention is the Navarro-Rizo conjecture. And I started by Brauer's-Height zero because I thought that it was a nice thing to do after Mandy's talk, but actually this is, I think, the first one in the literature, in my opinion, this Navarro-Williams conjecture. So they published a paper in 1997, and it's called When is a P block a Q block? And they try to analyze a very natural situation, which is if we have two sets of characters that are at the same time the irreducible characters on a P block, so BP is going to be a P block now of G, and the irreducible characters of a Q block, then can we say something of G? And this condition, I said that it appears naturally, and let me show you, for instance, one example. If we have, suppose that we have an irreducible character of the group which has P defect and Q defect 0 at the same time, so the P part of the degree is the P part of G, and the Q part is also the Q part of the degree. Then in this situation, we know that the P block containing the character contains just that character, and the same happens for the Q block. So in particular, they both are equal and are equal to this set of one character. So the P chi is the P block containing chi. The P chi is the Q block containing chi. And this is true. Okay? This is elementary, this is not very good. What they wonder is the converse also true? In the sense that if we know that the P block and the Q block coincide, then they necessarily have just one character. This is what they conjectured. Okay, so they conjecture this in this paper, and they, of course, they gave some evidence for this conjecture. They prove it if the group is P solvable or Q solvable. They also prove it in some more cases, and they said, and I quote, "We would like to remark that one should be able to prove the conjecture for principal blocks," but they don't prove it for principal blocks, but they say that there would be a reduction theorem, and then it would be a matter of checking these conjectures just for the simple blocks. The conjecture, as it is written here in the general form, is not true. Okay, and it was Christine Bessenroth who found a counterexample. So in 2006, he found an extension of A7, I think, where there were two sets of 5 reducible characters that were at the same time the reducible characters of a 5 block and of a 7 block. So this conjecture is not true, but in the same year, Bessenroth, Navarro, Olson, and Thiep proved the conjecture for the principal block. Prove the conjecture for the principal blocks, and I will restate it in a different way, like equivalent. So if the principal P block of G is the principal Q block of G, then they have just one character, but the principal P block having just one character is the same as saying that the order of the group is not divisible by P. So we are saying here that the order of G is not divisible by P, nor Q. So I use P prime, P prime. And I've seen in some talks some little proofs, and I like that, so I will try to make the short proof of the reduction theorem of this theorem. It's a nice theorem because it's very easy, and it's also a direct reduction theorem, so the conditions that we get is that we just need to check the theorem or to prove the theorem for simple groups. So prove the reduction. So we want to reduce it to simple groups, so we take, we suppose that our group is not simple, so we have it has a non-trivial normal subgroup N. Let me put it like this. So N is normal in G. And ideally, how a reduction theorem should work, but it's not usually the case, is that you can have your hypothesis in N and in the factor group G over N, and then you apply induction, and then you get your theorem in G over N and in N, and then somehow you recover your theorem for G. This is the idea behind the reduction theorem. And in this case, it works. So I want to prove that the principal P block of N is the principal Q block of N, and the same with the factor group G mod N. So we take an irreducible character in the principal P block of N, and then this is something that happens with principal blocks is that in this case we can always find, so I have my character in N, we can always have a character in G, in the principal P block of G, that lies over this character. That means that has tau in its restriction to N. Okay? So there exists one character in the principal P block of G above tau. Okay, the restriction of chi to N contains tau as an irreducible constituent. Okay, but now my hypothesis is that this is exactly the set of irreducible characters in the principal Q block of G. And another nice fact of the principal block of a group is that it just covers the principal block of any normal subgroup. So whenever we have an irreducible character in a principal block here, if we have a character in a normal subgroup under this character above, then this needs to lie also in the principal block of the normal subgroup. So in particular, lies in the principal Q of N, and now if we're taking the roles of P and Q, we will have that these two sets are the same. Okay, so we have the hypothesis for M, and now by induction, what we can say is that the order of N is not divisible by P nor Q. This is P prime. So now we need to verify also our hypothesis in the factor group G mod N, but now we have that our subgroup N is total to PRQ, and this is very strong in the principal block case, because in this case the characters of the principal block are exactly the characters of the principal block of G mod N. This is because is the principal block and N is contracted. So we are using N. But N is also compared to Q, so we can write exactly the same with Q. And we know that these two sets are the same, so we have that these two sets are the same, and again, induction, and we have, and this is P. So the result now just falls because G is P prime. So what we can assume is that G has no proper normal subgroups, and then it's simple, so we now need to check it for simple groups. Okay? And the last example that I want to mention, so I mentioned Browser 0 for 2 primes, the Navarro-Williams conjecture. And the Navarro-Williams conjecture deals with an extreme situation, no? Where a P block and a Q block coincide the principal P block and the principal Q block coincide. In this example, we see the extreme opposite situation where they just coincide in the trivial character. This is the trivial intersection situation. So, this situation is, as we said, where the principal P block and the principal Q block intersect with just the trivial character. Okay, the first thing in this situation where also this thin Besson and so on. And they did they proved a characterization of the nilpotency of the group in terms of trivial intersection. What they proved is that a group is nilpotent if and only if there is trivial intersection for all the primes, P and Q dividing the order of the group and different from each other. And actually they prove something stronger. So what they prove is that they prove something stronger, and what they prove is that if we fix one prime dividing the order of the group, then G is the direct product of the zero P subgroup of G and the P prime radical of G, the largest normal subgroup of G, of order not divisible by P, if and only if there is trivial intersection between the principal P block and the principal Q block for all the primes Q different from P dividing the. Okay? And as a consequence, of course, if we have trivial intersection from all the, for all the primes, then we have that all the zeros are normal, so the group is nilpotent. And just as a curiosity, this direction is elementary. So it does not require the classification of finite simple groups, but this direction requires the classification of finite simple groups. So now we have here the situation where we are running with all the primes dividing the order of the group, with the situation where we fix one prime and we run over all the other primes. But a natural question is what happens if we consider just two primes and we have trivial intersection between this principal P block and principal Q block? Can we still say something on the PQ structure of the group? And this is what these authors conjecture. So these are Liu, Willems, and they conjecture that if there is trivial intersection for P and Q fixed primes, then there is a nilpotent whole PQ subgroup. In other words, this is the CP subgroup and the CQ subgroup, which is the same as the right-hand side in the Gauss-Zero conjecture for two primes. Okay. So some remarks on this conjecture. The first remark is that it's a conjecture, so it's not proven, but they reduce it to prove it for almost simple groups. And they actually prove it when one of the primes involved is true. Okay. So now, these were the 3 examples that I wanted to mention, and now in the last 10 minutes, our results. So our work can be summarized as the height zero philosophy. So what is the height zero philosophy? Well, this is Amelia and Gabriel, and it thinks that basically we can replace, in all the examples that I mentioned before, the set of irreducible characters in the principal P block of G by those of height zero, which are the characters of the degree not divisible by P. So these are the characters in the principal block of the degree not divisible by P. Okay. So we tried to do versions of these 3 examples in this height zero setting, but we failed in general. We proposed 3 problems, 3 conjectures, that are the height zero versions of these 3 examples. So the first problem, the first theorem that I mentioned was Gauss height zero conjecture for 2 times. And remember that it says that pi P does not divide the degrees of all the characters in the principal Q block of G, and Q does not divide the degrees of the characters in the principal Q block of G if and only there is a zero P subgroup and a zero Q subgroup commutative. This was a theorem, as I stated now, but we think that this version should be true also. And some comments, of course, this direction is weaker, so this direction would follow just from the theorem, from the Malle-Navarro theorem, but this direction is in general much stronger, because these sets are in general much smaller than the sets of irreducible characters in the principal blocks. So I will give some evidences of these conjectures at the end, but let me state the other 2 conjectures. Sorry? P.
No, like for all your Q prime and BQ? Yeah, okay. But
I'm sorry.
yeah.
Thank you. Thank you. I also forgot. Okay. And the second example that I mentioned was the Navarro-Willems conjecture or theorem in the case of the principal block. And it said that if the principal P block of G is the principal Q block of G, then G is P prime and P prime. And again, we think that this should happen. And the last version is our version of the trivial intersection conjecture. Well, again, we replace these sets by the corresponding sets of height 0 characters. So I have 2 minutes maybe, and I will give evidence for this conjecture. So let me start with the last of them, because actually it was the first one that we attempted. So remember that they reduce it to almost simple groups and prove it in this case. We achieve the same. So we also reduce it to almost simple groups and prove it when one of the primes is 2. And I learned today that in the coffee break that one of the students in here is working actually in this conjecture in the other cases, so I'm very happy about it. And about conjecture A and conjecture B, well, when I finished my PhD, I received like a piece of paper of Gabriel with some ideas of possible projects that I could do in my first year of postdoc, and these were one of those problems. And in conjecture A, he commented that he thought that he could do the reduction theorem for this conjecture. And in conjecture B, he said that he didn't see the reduction theorem. So for me, I always thought during all my PhD that whatever work I do in, I don't know, months, Gabriel could do it in 1 day or so. So when I saw that he didn't see the reduction, that means, I'm sure that he didn't spend much time, but at least he didn't see it immediately. So I said, okay, I want to prove it myself, and I'm going to try this reduction theorem for this conjecture. And that's what I tried. And I realized that, okay, applied reduction was not possible, but if I use this conjecture, then I could do a reduction theorem. I sent to Mandy the conditions of this theorem, and she said that they were doable. So basically we proved at this point with Mandy that conjecture A will imply conjecture B. Okay, this is what we proved. We already use the classification heavily in here. We use it in the reduction theorem, and of course we need to check conditions on simple groups. Then I emailed Gabriel and I said, okay, I have this, and you said in your notes that this conjecture should be at least reducible to simple groups, so we tried to reduce it together. And what we found is that this conjecture is actually very hard to reduce, and we haven't been able to reduce it yet. But still we have this theorem, so we thought that if we give evidence for this conjecture to hold, then it would be good, because then it will also be evidence for this conjecture to hold. So we try to give this evidence, and we prove that conjecture A holds for big groups of double groups. Actually, I'm weaker than this, but it doesn't matter. And also for simple groups. So I think that this is it. Thank you.